Good morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar Series. In just a minute, I'll be thrilled to roll out, I believe, episode 109 or 1010 with Iman Marvian from Duke. And in this episode, we'll dive into a very fun topic on symmetric quantum circuits. Before we get there, we usually like to give people about a minute to tune into the live stream. And since we've had a little bit of a break, and now we'll be back with episodes every Friday at noon Eastern time, I'd like to remind you that you can always go back to these talks and rewatch them. You can know when the next one is coming by subscribing to the YouTube channel. But you can only ask questions live and interact with myself and Iman during the actual hour, Friday at noon Eastern time. So I encourage you to ask questions as we go throughout the talk, and I'll try to triage those and bring them up to Iman, and we can keep it a lively discussion. Usually people even answer each other's questions in the chat. So with that, folks, you can type where you're tuning in from today in the comment chat box, which is the same place we can communicate during this presentation. And I think it's time we begin. Today, I'm thrilled to roll out the latest episode of the IBM Qiskit Live Quantum Seminar Series dedicated to you, the research and academic communities. I am your host, Zlatko Minev from IBM Quantum Research, and today I have the pleasure and privilege of hosting Iman Marvian from Duke University, from the Department of Electrical and Computer Engineering and Physics. Iman received his PhD in 2012 at the University of Waterloo and the Perimeter Institute. Before moving to Duke, Iman worked as a postdoctoral researcher at USC and MIT. And Iman, as you don't have to guess, is the recipient of many awards, including the NSF Career. With that, Iman, it's a pleasure to welcome you here to the IBM Quantum Seminar.
Yeah, thank you, Zlatko, for the very kind introduction. And thanks, by the way, for the perfect pronunciation of my first name and last name.
We had a little fun backstage practicing to get it just right. So right. Appreciate that.
Thank you.
All right, the stage is yours.
Perfect. Yeah, I would like to thank the organizers for giving me this opportunity to talk to this community. It's a real pleasure. In this talk, I'm going to present some results about an ongoing project on symmetric quantum circuits. I started this project around 2 years ago, or more than maybe 2 years ago, but it has been so fascinating that I'm still actively working on it, and I would like to talk to this community about some of these results and some of the open problems. So in this project, we study various properties of quantum circuits that are formed from gates that respect a certain symmetry. For example, they are all invariant on the rotation around Z, for example. And then we study various properties of this kind of circuits. What are, their statistical properties of random circuits, for example, with these properties, and other types of questions. But, the very basic question, the first step in this project is just to understand the question of universality. So we know, according to one of the most fundamental results in quantum circuit theory, that any unitary transformation on n qubits or n qudits can be realized by a finite sequence of two local gates that act on at most 2 qubits or qudits. So this result, was discovered, I think, in around 94, 95 by DiVincenzo and Lloyd. There were earlier works by Deutsch in 80s. It's, by the way, very interesting that this result was not known when Peter Shor discovered his factoring algorithm. But in my mind, although this result was discovered in the context of quantum computing, but this actually captures a much more fundamental fact about dynamics of systems with composite systems with local Hamiltonians. So we know that locality of interactions impose various types of constraints on the time evolution of a composite system. For example, locality implies finite speed of propagation of information, as is captured by Lieb-Robinson bound. And, so it means that the information cannot propagate arbitrarily fast in the system. But this universality of two local gates means that if you give the system enough time, then in principle, any unitary transformation is realizable. And therefore, the locality of interaction doesn't restrict the long-term time evolution of the system. It restricts the short-term time evolution, but not the long-term time evolution. Now, the first basic question that I asked in this project is what happens in the presence of symmetries? And in particular, does the universality of these two local gates remains valid in the presence of symmetries? So clearly, if all your gates are restricted to have a symmetry, for example, they are invariant on the rotation around Z, then you can only implement unitaries that respect the same symmetry. You cannot break that symmetry. But now the question is, can you realize all unitaries that respect the symmetry using local unitaries that respect the symmetry? Okay? In other words, do local symmetric unitaries generate all symmetric unitaries or not? So, of course, this is just words. I will come back to this exact question, and I will formulate it more precisely with some formulas. But this is the intuition. So we want to understand, in this first step of this project, we want to understand what is the set of realizable unitaries with K local, for example, symmetric unitaries. Okay, so here is the overview of the rest of my talk. I will talk about motivations and applications briefly. Then I will present some kind of surprising result for me, at least was surprising. It was non-universality of local symmetric unitaries. And then I will present some results about characterizing symmetric unitaries in the case of U1 symmetry and SU2 symmetry. And then at the end, I will talk about some results in the case of SUD symmetry. Again, we see that in the case of SUD symmetry with D larger than 2, for example, SU3 symmetry, there's some sudden very different behavior from, for example, SU2. So there is, again, another surprise when we go to SU3 symmetry. So the results that I present in this talk are mostly based on these three papers. The second, third paper here are joint work with two bright students. Hanqing is a former student, Hanqing Lu and Austin Hals at Duke University. Okay, let's start. Let's first talk about motivations. Why we should study local symmetric quantum circuits. One, first of all, this family of circuits has already become a standard tool in in theoretical physics. They are used, for example, in different areas of condensed matter theory. For example, to study to classify symmetry-protected topological phases. Symmetry-protected topological phases are classified based on low depths or shallow symmetric quantum circuits. Or they are used, for example, to study quantum chaos in the presence of conserved charges and scrambling of quantum system, scrambling of information in the presence of conserved charges. And I would say that, it's kind of embarrassing for us that we still don't fully understand what's going on in symmetric quantum circuits. What are, for example, the unitaries that we can implement just with circuits that respect the symmetry? But there are also some immediate implications and applications to study this problem. First of all, we can, by studying dynamics of systems under local interactions that respect the symmetry, we can possibly find new conservation laws that constrain the dynamics of the quantum system in the presence of both symmetry and locality. We know that symmetry itself impose some conservation laws. For example, rotational symmetry implies conservation of angular momentum. But now the question is, if you know that in addition to the symmetry, rotational symmetry, for example, you also have locality of interactions, do these together, when you have both of these properties together, do they imply any additional conservation laws or not? So this is one sort of question that you can understand, you can answer, finding new conservation laws that hold the presence of both symmetry and locality. The second motivation comes from the area of quantum thermodynamics and quantum resource theories more generally. In particular, the resource theory of asymmetry, quantum reference frame, and also the very closely related topic of covariant error correcting codes or continuous quantum error correcting codes. And in all these areas that I've listed here, often we need to implement a unitary transformation that respects the symmetry. For example, in quantum thermodynamics, we need to implement unitaries that respect that conserve the intrinsic Hamiltonian of a system. So we call them energy conserving unitaries. And similarly, in resource theory of asymmetry, for example, is assumed that you can easily or with negligible cost, you can implement an arbitrary symmetric unitary. But now the question is how we can really implement them. If you have multiple systems, if you have a composite system with many components, can you implement a general symmetric unitary on this system by acting locally on subsystems or not? And if you think about it classically, at least, the intuition is, in principle, you can redistribute energy of the system. Let's say you have 3 systems, for example, here, and each of them has its own intrinsic Hamiltonian. You should be able to redistribute the energy in the system just by a sequence of steps that couple pairs of systems together. So you don't need to really do something fancier than that. And so just this intuition suggests that maybe all energy conserving unitaries, all unitaries that respect the total Hamiltonian of these 3 systems, should be realizable by a sequence of 2 local energy conserving unitaries. Okay? But if this is not the case, then maybe there is some hidden thermodynamic cost for implementing a general energy conserving unitary using local energy conserving unitary. Okay? And the third motivation that I've listed here is coming from the problem of synthesizing noise-resilient quantum circuits, or in other words, more generally, fault-tolerant implementation of a unitary transformation. Generally, we can take advantage of symmetries of a unitary transformation to find more noise-resilient implementation of that unitary transformation. For example, unitaries that respect that conserve the intrinsic Hamiltonian of a qubit or a set of qubits, they are less sensitive to noise that is generated essentially by fluctuations of the master clock that controls the timing of these pulses. For example, just a single qubit rotation around Z is less sensitive to this, fluctuations, whereas a Hadamard that doesn't conserve the intrinsic Hamiltonian in Z direction is more sensitive to these fluctuations. So, and now the idea is, can we take advantage of these symmetries that a unitary or a subroutine that we want to implement in a quantum circuit, can we take advantage of them and find an implementation that is more robust against this kind of fluctuations? So the standard circuit synthesis techniques ignores this symmetries. Just you decompose a desired unitary transformation to a set of CNOT, Hadamard, T-gate, but how the question how we can take advantage of these symmetries. And here is a concrete example. There is a family of unitaries generated by multi-qubit swap Hamiltonian. So this is a useful subroutine in various quantum algorithms, including QPCA in this paper from 2014. So this family of unitaries essentially implement the swap Hamiltonian. So swap is, of course, a unitary, but it's also a Hermitian operator, so you can think of it as a Hamiltonian. Now, think about this multi-qubit swap Hamiltonian. I have 4 qubits, 2 qubits in system A, 2 qubits in system B, and I want to swap A1 with B1, A2 with B2. So this operator, as as a Hamiltonian, generate this family of unitaries, exponential of swap. And so the question is how we can implement this family of unitaries. And in particular, the fact that this family of unitaries respect SU2 symmetry and respect even also U1 symmetry, can we take advantage of this? And can we implement this family of unitaries just with unitaries that respect SU2 symmetry or at least U1 symmetry? Maybe we need to break the SU2 symmetry of this problem and just realize it with gates that respect the U1 symmetry. So this is a question that I will answer this in this talk. Okay, now let's try to start formulating this problem. This will be my running example. So a system with n qubits with U1 symmetry. For a system with n qubits, so here U1 symmetry, I'll think of it as rotations around Z. So Z is here Pauli Z operator, and I am assuming that unitary V commutes with the action of the rotations around Z. Or equivalently, this is a unitary transformation that conserves some of Pauli Z operators, or in other words, conserve the Hamming weight. And so the goal is to implement this family of unitaries. In the case of a single qubit gate, for example, these are all diagonal unitaries. In the case of two qubit gates, there's essentially three sectors: sector with Hamming weight 0, sector with Hamming weight 1, and sector with Hamming weight 2. And you can have arbitrary phase in this sector with Hamming weight 0, and arbitrary phase here in sector with Hamming weight 1, and arbitrary 2x2 unitary in sector with Hamming weight 2. And then in the case of three qubits, you have four sectors: Hamming weight 0, 1, 2, and 3. But now here you have 3x3 unitaries in these sectors. And now here's the simplest version of the question that I want to study. Can I implement a general unitary transformation acting on 3 qubits that respect the symmetry, this 8x8 matrices, using just 2 local unitaries? So unitaries in this form of n equal to 2 that couples pair of qubits. Can I implement a general unitary acting on 3 qubits using pair of unitaries that are acting on pair of qubits? So let me pause here and see if there are questions, because this is essentially set up the problem and define exactly the question that I want to study in the rest of this talk. So if there are questions now, it's a good time to ask.
Yeah, and I guess here you allow yourself any single qubit operations that you can mix in anywhere you want.
Any single qubit operation that is diagonal in Z basis.
Okay, but you will restrict yourself to not have X or okay, I see.
Yeah. I only have rotations around Z essentially. On 2 qubits you have so on 1 qubit is just rotation around Z, so it's quite very boring. But on 2 qubits you can have more interesting things, because in this 2-dimensional subspace with Hamming weight 2, you can have an arbitrary 2x2 unitary. V1 can be arbitrary unitary.
Okay, yeah. I guess there's maybe this might be jumping. You feel free to push this question to later. What if you restricted your multi-qubit unitaries to have a symmetry, but then your single qubit unitaries could, be basically anything? I imagine then you still have some restriction, but I feel like this question is coming too early, so we can save that to later if you'd like.
Yeah, no, I mean that's a good question. If you can break the symmetry on 1 qubit, then essentially you can do anything. Well, let me see. Yeah, I think you can do anything because you can create. You can use just the type of family of unitaries that I mentioned before, that generated by Hamiltonian swap. You can use them to create entanglement, and then you can have arbitrary single. So you have an entangling gate that respect the symmetry, and then you can also have arbitrary single qubit gates. So then you can generate essentially any unitary. There's no restrictions.
Excellent. Okay, thank you.
Sure. Any other questions?
Yeah, folks, this is a great time to post questions in the chat, which I'll make sure to look up.
Okay. If there are no questions, then I can go next step. I cannot see the chat. So if Zlatko, please let me know if I should move on, or I should go to the next slide, or.
Oh yes, go ahead.
Okay. Okay. So I formulated this question in terms of quantum circuits. Unitaries that act on 2 qubits or k qubits, for example. But equivalently, I could have formulated this problem in terms of continuous time evolution under Hamiltonian. So let's consider a system of qubits or qudits that are sitting on form a spin chain, for example, and then they are evolving under Hamiltonian in this form, that HT that can be decomposed as sum of k local terms, right? And then I require that the Hamiltonian should also respect this U1 symmetry, should conserve some of Pauli Z operators. And then I look at what the family of unitaries that can be generated in this way under the Schrödinger equation. And then, using the standard results of control theory, you can argue that the set of unitaries that can be implemented in this way, in the right-hand side, in the continuous dynamics, is exactly the same as the set of unitaries that can be implemented just by discrete circuits, right? So these two pictures are, these two questions are essentially equivalent. Also, let me mention that here I'm using the notion of k-local gates, so there is no geometry here. This k-local operations can couple any pair of any k qudits together. But you may think that maybe if I impose locality, a stronger notion of locality, geometric locality, then it may change the problem. But it doesn't actually, because you can see that if you're, for example, sitting on you have a spin chain with nearest neighbor interactions, let's say, for example, k equal to 2, just using swaps, you can arbitrarily change the order of these qubits, and essentially then the geometry of the particular geometry that becomes irrelevant, provided that you have a connected graph, of course. So imposing the stronger constraint of geometric locality doesn't change this problem really. So the set of realizable unitaries will be essentially the same. Okay. Now I also should mention that I set up the problem in the case of U1 symmetry, but of course you can define it for general symmetry group G. And in principle, you can imagine that this group has different representations and different subsystems. And then you can ask, what are the set of realizable unitaries on the entire system, and what are the set of realizable unitaries by composing k-local symmetric unitaries. Okay. So here is the first result, non-universality of local symmetric unitaries. It turns out that in the case of continuous symmetries, such as U1 symmetry that we discussed, generic symmetric unitaries cannot be implemented using local symmetric unitaries on the subsystems. So it's a strong no-go theorem. I will show more quantitative version of this no-go theorem, by the way, in the next slide, but this is the message. And now you may think that maybe I cannot implement the desired unitary, the desired symmetric unitary exactly, but maybe I can implement it approximately. But again, it turns out that the answer is no, because it turns out that the group of symmetric unitaries and a subgroup generated by k-local symmetric unitaries are both compact connected Lie groups. And this essentially means that the relation between these two groups can be schematically represented by this figure. So you have a torus, which corresponds to the group of all symmetric unitaries, and you have this helix, blue curve that's going around, which corresponds to the subgroup generated by k-local symmetric unitaries. And so the point is, this helix doesn't get arbitrarily close to all points on the torus, and so you can't, which means that essentially you cannot implement a generic desired symmetric unitary with arbitrary precision. And we will see that the gap between the dimension of these two manifolds, the manifold associated with all symmetric unitaries and submanifold corresponding to generated by local symmetric unitaries, the gap increases with the system size. Okay, so here is a more quantitative version. So this is again about the example of U1 that we discussed before. So it turns out that the difference between the dimension of the group of all symmetric unitaries, so the first one here is the group of all symmetric unitaries, and the subgroup generated by k-local symmetric unitaries is n minus k. So k is again the locality of these gates. And so you see, unless k is equal to n, which means that your gates are acting essentially on the entire system, it's not possible to generate a general U1 invariant unitary using k-local U1 invariant unitaries. So this number, the right answer, n minus k, has a, you can interpret it as the maximum charge that can be in the system minus the maximum charge that can participate in interaction. So k will be the maximum charge. So now let's look at that example that I discussed before, 3 qubits. So this 3 qubit example is about 8 by 8 matrices, but even in this example, it's non-trivial. So it turns out that group of all U1 unitaries is 20-dimensional, but the subgroup generated by 2 local U1 invariant unitaries is 19-dimensional. So here you have 20 minus 19 is equal to 3 minus 2. K here is 2, so the identity holds. And to have a concrete example, the family of unitaries generated by this family of unitaries, unitaries generated by Hamiltonian Z tensor 3, they cannot be generated using 2 local U1 invariant unitaries, except maybe a finite set of unitaries in this family. Okay. Now, here's the example of SU2. In the example of SU2, it turns out the similar formula holds. It's slightly more complicated, but it's essentially similar. The difference in dimension of the two groups is integer parts of n half minus integer parts of k half. Again, this VK SU2 here is this is the group generated by k local SU2 invariant unitaries. Okay, so if you remember the example of this multi-qubit swap Hamiltonian that I discussed before, it turns out that in this case, this family of Hamiltonians, the Hamiltonians that are generated by this multi-qubit swap, they cannot be realized with two local rotationally invariant unitaries. Okay, so the answer to the question that I asked before, they cannot be realized with is no, and this family cannot be realized. And I won't go through the details of why it should be, why this is true, but let me just mention that in this example, it turns out that if the family of unitaries that can be realized on 4 qubits and respect SU2 symmetry, they should satisfy this additional constraint. So here pi j is a projector to the subspace with angular momentum j, and so it turns out that this particular linear combination should be 0 with this integer coefficient to be realizable with two local SU2 invariant unitaries. So this particular constraint comes from the locality of the interaction, essentially. And this Hamiltonian, the swap Hamiltonian, doesn't satisfy this constraint, so it's not realizable. So I talked about two examples, U1 and SU2. Here is the more general results. For general group G, the difference in the dimension of two groups is lower bounded by this the right-hand side. This is the number of inequivalent irreducible representation of group G that appears on n system, the entire system, essentially n qubits, the entire system, minus the number of inequivalent representation of group G that appears only on k subsystems or k qudits. So just to explain how it relates to the result that you saw previously, when you think about group U1 on n system, you have n plus 1 different inequivalent representation of group U1 corresponding to Hamming weight 0, Hamming weight 1, all the way to Hamming weight n. So these are n plus 1 inequivalent representation of U1. And on k system, you have k plus 1. And so in the right-hand side, you have n plus 1 minus k plus 1, which is n minus k. And in general, in the case of Lie groups, if G is a Lie group like U1, SU2, this number of irreducible representation can grow unboundedly with the system size, whereas this number, irreps of GK, this is a fixed number, it's independent of the system size. So this immediately implies that in the case of continuous symmetries, you cannot achieve universality with any fixed k, because the right-hand side essentially always grow with the system size. Let me pause here again for a second if there are questions.
Maybe you'll touch on the connect. I think I might be anticipating again later part of your talk. You'll touch on the connection between this and physical systems, or things like many body dynamics and so on. I imagine that's coming up.
Yeah, I will tell a little bit about that. Any other?
I think that's good for now.
Okay, so now, this is in essence a no-go theorem. It's of course very interesting to me, at least. It's a surprising fact, but does it have any implications or applications? So here is a quick, kind of, I think, interesting application of this result. It says that in the presence of symmetries, we can probe the locality of interactions in the following sense. So suppose I have a unitary transformation, an unknown unitary transformation that corresponds to an interaction between some subsystems. And so now the question is just, can I, by probing the different and the behavior of this unitary transformation for different inputs, and by looking to its output, essentially, can I determine whether this unitary transformation, this process, contains any three-body interactions in it or not? Right? Is there any three-body interaction going on in this black box or not? And then, it turns out that in this sense, the standard, universality results that we know, by that two local unitaries are universal, it implies that no, it's absolutely impossible. If you just by looking to the output for different inputs, you can't say whether there's a three-body interaction going on in this process or not, because any unitary transformation is realizable with two-body interactions. But on the other hand, in the presence of symmetries, this no-go theorem tells us that yes, in the three-body interactions, for example, have certain signature that is not reproducible by two-body interactions. And just by looking to the output, for different inputs, then you can see that signature, you can detect that signature, and so you can detect the presence of three-body interactions in this unknown process.
Sorry, quick question. Let me see if I understand this. If I had why couldn't I just do? Given any number of inputs and measuring all the outputs, doesn't that mean that I can just do full quantum process tomography?
Exactly.
And then
you find the description of unitary U.
Yes.
But now the question is that, is there any three-body interactions going on in this unitary process or not? And
because if I take the, I guess, and the logarithm is not unique, but if I take the logarithm and try to find the generator, you're saying that there are many different decompositions, and so it's hard to know which one gave right to it.
Exactly. And why we know that is just follows from the universality of two local gates, that when you look at the logarithm, you see some non-local, in general non-unique Hamiltonian. But the question is, can it be realized with, do you need three-body interactions to realize, for example, that logarithm or not?
Mm-hmm.
And the universality result tells us that no, you don't need to.
But couldn't I cheat? Because what if I can control the time, then I can set the time to be very, very short, in which case, this unitary is almost the Hamiltonian. It's, I minus, is the identity minus epsilon times the Hamiltonian, effectively. And then wouldn't that allow me to directly access the Hamiltonian? It wouldn't be very efficient, and it wouldn't.
No, I agree with you that adding certain, if you can open this box, for example, if you can exactly see what's going on each step in time, you can certainly distinguish between two local and three local interactions. That's certainly possible. But if you make some assumptions about the strengths of the interactions, etc., that's possible. But just this, in this black box form of this problem, that if somebody gives you this unitary and asks if what's going on inside this process, you can't say that. And the point is, in the presence of symmetry now, you can say something.
I see. Okay. So basically, we're saying I don't have control to the time knob for this.
Yeah. Yes, and so the point is, even if you have the control, you need to make some assumptions about the strengths of the interaction. Maybe there is a three-body interaction, so making some just control over time, I don't think is enough. But I agree with you that adding some assumptions, like in addition to that, then you will be able to distinguish between two local and three local in principle. I guess the emphasis here is that with symmetries, you can do even more. You don't need to make any of those assumptions. You don't know anything about the details, but you can see the signature of three-body interactions.
Yeah. And this, I guess this also reminds me, and maybe I'm jumping again, but it also reminds me of these many-body localization discussions where maybe there's symmetry that, means that you have... Anyway, maybe I'll let you finish here first and get into that.
Sure. Okay, so yeah. Now this results somehow made me worried because I worked on this, quantum thermodynamics. I've worked on the resource theory of asymmetry, and in all these theories, the first defining assumption is that, for example, in thermodynamics, the assumption is that you can implement any energy conserving unitary for free, regardless of the number of subsystems. You can assume that you can do it in an IID regime. And so then this result suggests that maybe this is not a a realistic assumption. Maybe this is not a good assumption, because in the context of this U1 symmetry that we are discussing, so this can be interpreted as conservation of energy, and so you cannot. Another way to interpret this result is that you cannot generate a general energy conserving unitary using two local energy conserving unitary. So, but fortunately, it turns out that at least in some cases, you can circumvent this no-go theorem using ancillary qubits. So in the case of group U1, this no-go theorem can be circumvented using an ancillary qubit. Just a single ancillary qubit is actually enough. So for any unitary V on n qubits, there's this unitary V tilde acting on n qubits such that it's essentially when it acts on your system and an ancillary, which is initially prepared either in 0 or 1, it realizes unitary V on the system for arbitrary state psi. So the ancilla should be either in say 0 or 1, and you need to know which one actually. And indeed, it turns out that you can realize a general U1 invariant unitary using just XX plus YY interaction and single Pauli Z, which are both invariant under rotation around Z, provided that you can interact with these ancillary qubits. For example, if you can put even your qubits on a chain with nearest neighbor XX plus YY interaction, provided that they can interact with this ancillary qubit, also with XX plus YY interaction, then you can realize any unitary transformation in this way, any U1 invariant unitary transformation in this way. Or, if you allow ZZ interaction, then you can just have nearest neighbor interactions and you can put your qubit on one end of the chain, your ancillary qubit. Okay. So in the context of quantum thermodynamics, there is this more general, I showed this more general result that first of all, the no-go theorem implies that generic global energy conserving unitaries cannot be implemented using local energy conserving unitaries. But then I showed that, again, you can circumvent this no-go theorem by using an ancillary qubit, or to be more precise, an ancillary two-level system. So I just read the statement of the theorem. Consider finite set of closed system with property that for each system, the gap between any consecutive pair of energy level is delta E. Then any global energy conserving unitary transformation on these systems can be implemented by finite sequence of two local energy conserving unitaries, provided that one can use a single ancillary qubit, which can be interpreted as catalyst, with energy gap delta E between its two levels. Okay. So at least for applications in quantum thermodynamics, this is good. Like this is I think a useful result that says we are safe. The assumption that energy conserving unitaries can be implemented is safe. So it turns out that you can extend this result also to case of SU2 with two qubits, two ancillary qubits. Any rotational invariant unitary V and qubits can be implemented using just Heisenberg interaction, which is two local and respects SU2 rotational invariant interaction. And you just need two ancillas. The ancillas, two qubits, they can be initially prepared in a state 0, or they can be in the singlet state. And they don't need to be, it can be singlet, or it can be any state in the triplet subspace, including, the maximum mixed state in the three-dimensional space of subspace of corresponding to triplet. But you need to know which one you are given. So in other words, you don't need to break SU2 symmetry to realize, rotational invariant unitary V as we expect. Okay, so this was about U1 and SU2, and now I want to talk about qudit system with SU dissymmetry. If there are questions, again, maybe this is a good time to ask.
I'll save them to the end.
Okay. So, this is again a very natural question. What happens about SU dissymmetry, which is again is relevant for many physical systems? So here, parameter D specifies the local dimension of this subsystem, so the dimension of each qudit, and it's also specifying my symmetries. So the total Hilbert space is n copies CG tensor n copies of n qudits, and then I look at unitary transformation that commutes with U tensor n for arbitrary unitary acting on a qudit. It turns out that in the case of, in this case, two local unitaries, up to a global phase can be written in the form of e to the I theta swap. So PAB is essentially the swap unitary, exchange the states of two systems. And up to a global phase, any two local SU2 invariant unitary is in this form. So in other words, the question that I'm asking here is that, can I compose this type of unitaries that acts on a pair of qudits? And can I implement a general unitary that respect this SU2 symmetry just by composing this, so I choose different A and B, different pairs of qubits and different angles, thetas, and can I generate an arbitrary unitary transformation that respect SU2 symmetry? Or equivalently, you can ask, what is the family of unitaries that can be realized under this Hamiltonian? So Hamiltonian is a linear combination of these swaps with possibly time-dependent coefficients. What is the family of unitaries that are generated this way? And here again, we found something that was surprising to me. It turns out that there is an important distinction between the case of d equal to 2 and d larger than 2. So in the case of d equal to 2, which is SU2 symmetry that we discussed before, SU2 with qubits, locality only restricts the relative phases between different conserved sectors. Whereas for d larger than 2, in addition to those constraints on the relative phases between different sectors, there are also some restrictions inside each subspace, inside each conserved subspace that is imposed by locality of interactions. So let's talk about a concrete example. So this is a 6 qubit example. So here d is equal to 3. So I have 3 of my qubits are in state 0. So here 0, 1, 2 is an orthonormal basis for a qubit. And the 3 other qubits are in a state singlet. So this is a totally antisymmetric state of 3 qubits. And it turns out that for this state, the joint state is restricted to a subspace with a single irreducible representation of SU3, right? And so here is an interesting phenomenon. If you allow an arbitrary SU3 invariant unitary in this system, then this initial state can go to any superposition in this form. So this is a superposition of the original state plus the state that is obtained from the original state by swapping the first 3 qubits with the second 3 qubits. So anything like that is allowed under SU3 invariant unitaries because essentially these two states are breaking the SU3 symmetry exactly in the same way. On the other hand, if you restrict yourself to 2 local SU3 invariant unitaries and ask what type of states in this subspace I can generate, then the only states in this two-dimensional subspace that you can obtain are either the original states, obviously, or the state that can be obtained by just swapping the first 3 qubits with the second 3 qubits. You cannot generate superpositions in this form. Right? So in this two-dimensional subspace, you can only go to this or this under 2 local. And again, interestingly, it turns out that if you allow another 3 qubits as a catalyst, again in the singlet state, now you can overcome this restriction and you can generate these superpositions, and then you can return these 3 qubits in their original state. So it's really a catalyst. It doesn't change. Okay. So here you see an example of type of restrictions that are caused by locality. That creating these superpositions are impossible because of locality. And it turns out that this type of restrictions can be understood in terms of a type of new conservation laws. So conservation laws that are not the standard Noether's type conservation laws that we are more familiar with. So here, let me give you an example of those conservation laws. So this is related to a very interesting Z2 symmetry in this problem. So think about the family of unitaries that I discussed before, e to the I theta swap. So PAB is again swap operator acting on qubits A and B. So you can decompose it in this way. And when you look at this decomposition, you see that the first term in this decomposition, cosine theta, is a real term, and the second term is purely imaginary. And at the same time, another thing happens. Identity here is an even permutation. It has even parity, and swap has odd parity. So even parity comes with real matrix. Odd parity comes with a pure imaginary matrix, right? And then when you multiply this, unitaries, you will see that this pattern survives. Always, even parity permutations comes with real coefficient, whereas odd parity permutations comes with purely imaginary coefficients. And for example, if you write down these matrices in the computational basis, you will see that this being real, it will be correlated with being even, and being odd is correlated with being purely imaginary. But I mean, we should be a little bit more careful about this analysis because permutations in general are not linearly independent. For example, for a pair of qubits, you have this fact that you can have linear combination of even permutation. Linear combination of even permutation in the left-hand side, which gives you odd permutation. So this distinction between even and odd makes sense if you have your dimension is large enough. But anyway, it turns out that there are this phenomenon, this type of Z2 symmetry is related to a conservation law. So you can impose a conservation law. Here is a function, FSGN, is a function that is conserved because of this property that I just mentioned above. It's defined as 1 over n factorial. The summation is over all permutations on n qubits in the system. P sigma is permutation, is the representation of the permutation, and SGN is just the parity of that permutation, which is either +1 or -1. This function has a simple interpretation. You can, if you think about two copies of a state psi in the state of the system, this function is essentially the probability that these two copies is in the totally antisymmetric state with respect in the totally antisymmetric subspace with respect to permutations of these pairs of qudits. So you have an action of Sn on these pairs of qudits, and then the question is, what is the probability that you are in this totally antisymmetric subspace? This FSGN determines that probability. So in particular, it's a number between 0 and 1, and it turns out that it's conserved because of this type of Z2 symmetry that I just mentioned above. So we observed this through math, but we didn't really believe it until we did the simulation. So we looked at a system with, again, 6 qubits in this initial state. So this is a totally antisymmetric state again. Of the first 3 qubits, antisymmetric state of 4 and 5, and the last state is in 0. So this is the initial state. The initial state doesn't really matter, but so we let the system evolve initially under 2 locally symmetry-invariant unitaries, and then we see that this function, which happens to be 0 for this state, remains 0 for all times under 2 locally symmetry-invariant unitaries. But at this point, at t equal to 100, we turn on a 3-body interaction now, and then we see that the function is not conserved anymore, so it's self-evolving. And then at t equal to 300, we turn on another interaction, which is now 4 local. It acts on 4 qubits, but still respect that Z2 symmetry that I mentioned before. And again, it turns out that this function remains conserved. So this clearly demonstrates that conservation law that I was talking about. Now, it turns out that this problem of SUD symmetry with qubits is actually a very rich problem. There's a lot going on in different Europe's, some in different sectors. Essentially, roughly speaking, you can, divide the type of constraints that are caused by locality in this problem to 3 different types. So you have constraints on the relative phases between sectors with an equivalency with the sort of representation of symmetry. You have constraints related to a Z2 symmetry that I just mentioned before. It turns out that there is also constraints in certain sectors. The dynamics of the system can be mapped to a fermionic system. And it turns out that if for 2 local unitaries, the fermionic dynamic will be the dynamics on the free fermionic system. Whereas if you allow 3-body interaction, for example, then it will be not interacting fermionic system. And then you can see the difference between these 2-body and 3-body interactions by looking to that fermionic system. So we present these results, in this archive paper here. I should mention that there's a problem that is previously studied, a closely related problem that is previously studied in the math literature in this French paper. This works obtained the decomposition in simple factors of the Lie subalgebra of the group algebra of the symmetric group generated by the transpositions. So it turns out that, you know, some of the results that are obtained in this paper is essentially have a very simple, using very advanced technique that's hard for me to understand. They have a very simple interpretation if you think of them in terms of a result about fermionic system. So, you know, there's, for example, a mysterious result that you see in certain sectors of SUD, you have a very restricted behavior. And then when you think about this problem in terms of fermions, you will see that this is exactly because this fermion, this is a non-fermionic, this is non-interacting fermionic system. So I don't go through, my time is almost over, so I don't go through the the exact details of this fermionic mapping, but it turns out that, you know, by just studying quantities that remain conserved under non-interacting fermionic dynamics, you can find new conservation laws, and which are independent of, you know, the conservation laws that I mentioned before in the case of Z2 symmetry. Let me also briefly talk about random symmetric circuits. My time is almost over, so I won't go through much details. But here the idea is, you know, we know that unitary transformation. So the question is, what is the distribution of unitaries that are generated by, if you randomly choose two local or k local SUD invariant unitaries and compose them together? Can you, in this way, can you generate the uniform distribution or hard distribution over all symmetric unitaries, or over all, in other words, SUD invariant unitaries? Can you generate a hard distribution over all SUD invariant unitaries or not? And it turns out that the answer is no. And it turns out that you know, the family, because of the conservation laws that I just mentioned, the family of the distribution that is generated by random two local SUD invariant unitaries is not even a two design for the hard distribution over the group of all SUD invariant unitaries. And being two design is, essentially means that even the second moments of the distributions are different. So and this is a consequence of just the conservation laws that I mentioned before. Okay, let me stop here and summarize. If there are questions, I will be happy to go into more details. So in summary, we saw a strong no-go theorem in the case of continuous symmetries that implies any generic symmetric unitaries cannot be implemented, even approximately, using local symmetric unitaries. We said that the difference between the dimensions of the two manifold is lower bounded by this, the difference between the number of irreps, irreducible representation, inequivalent irreducible representation that appear in N system and K system. In the case of U1 symmetry and SU2 symmetry, both of these bounds hold as equality. And in these two examples, all the constraints caused by locality are constraints on the relative phases that can be created between different sectors with different charges. And in these cases, you can use, you know, these no-go theorems, or essentially as a way of detecting or probing the locality of interactions in an unknown unitary. We saw that we can circumvent this no-go theorem. In the case of U1 symmetry, you can implement any any U1 invariant unitary and qubits using XX plus YY interaction and single Z, qubit Z. And in the case of SU2, you can implement any SU2 invariant unitary and qubits, including, for example, that family of unitaries generated by a swap Hamiltonian, a multi-qubit swap Hamiltonian, using just Heisenberg interactions and two ancillary qubits. And in the case of SUD symmetry, we see that there are, you know, additional conserved quantities, even for states that are restricted to a single irreducible representation, a subspace with a single irreducible representation of the symmetry. You will see these new conservation laws that restrict the time evolution of the system. Let me stop here and be happy to answer any questions.
Thank you, Iman. Very nice. Maybe first question from Kelly. From one of the earlier slides, you made the comment that circuits that contain only energy conserving unitaries are less sensitive to fluctuations. Can you quantify this, or is there some relevant figure of merit?
Yeah, I mean, if let's say, for example, if you want to implement a Hadamard that doesn't preserve the energy, then you can quantify it by thinking of there are works that have basically quantifies these fluctuations in the phase of the master clock, or in terms of the power density of the noise, and that immediately translates to essentially a dephasing noise. But the point is, because the energy conserving unitaries commute with the effect of this noise, they don't essentially propagate it through the circuit, and the action of that particular gate essentially is not affected by this. So there are ways of quantifying this just by thinking about the noise as a random rotation around z-axis. So let's say, and here all the qubits are randomly rotated, let's say by the same angle, because they are controlled by the same clock, and then that translates to a dephasing noise. But this is a problem that should be studied further to understand exactly how, to what extent, so to exactly quantifying this problem and seeing the effect of using symmetric circuits is a problem that requires further investigation. But in principle, just because the gates commute with these random rotations around z-axis, they are less sensitive to the implementation. They are less sensitive to the this type of noise.
Okay, wonderful. And Kelly, feel free to follow up in the comments if there was more to that. Kelly says thanks. Great. One more quick question: have you thought about this ancilla-based method versus using native k-local gates, and how these procedures might differ in the presence of noise in kind of NISQ quantum computers? If one could then effectively benefit from this procedure, or you'd require some level of fidelity of your gates?
Yeah, I mean, just going back to the last question and comment, I think it's let's say for certain subroutines, like this family of swap Hamiltonians, the unitaries generated by swap Hamiltonians, that are useful for quantum algorithms. I think even in the NISQ regime, it could be useful to think about their implementation using gates that respect symmetry. Like, say, for example, they are here in particular, we can think about the U1 symmetry, which is again relevant because of energy conservation, because it guarantees less sensitivity with respect to fluctuations of a master clock. So I think, yes, even in the NISQ regimes, for certain subroutines, this technique can be useful. If your subroutine enjoys the symmetry, has the symmetry, let's use that in the design of the circuit. And then you can use a single ancilla qubit, or maybe even more ancilla qubits if it makes it more efficient. And then implement it using gates or using modules, maybe not single qubit, maybe your single qubit gate doesn't respect that U1 symmetry, but maybe you can combine it with another gate such that that submodule respect the U1 symmetry, and then compose these modules that respect the U1 symmetry to generate a subroutine like this, or a family of unitaries like this. I don't know if I answered the question.
Yeah, hopefully. I feel free, folks, to follow up on that, and to post any final questions as we really come to the end of the hour. I think I've really enjoyed this. Are there any other maybe last words you want to share with us around the implications of this really nice work to quantum many-body systems, things like chaos, scrambling, and localization, or the ETH hypothesis.
Yeah,
I'm throwing a lot at you, but
this is a fascinating question that I'm still trying to understand. So the short answer is I don't know, and I'm interested. I'm working on this. We will see. I mean, I still don't know if there are implications. I think this is something that is worth investigating. Because, for example, there are these conservation laws, for example, in the case of SUD, symmetry, and they can have certainly they can possibly slow down the thermalization of the system. They can be an obstruction toward scrambling of the information or slow down. And I think, but I still don't know to what extent this will be a serious effect. Sorry. Sorry, can you hear me?
Let's see, I got muted. Any final thoughts or notes you wanted to share with the audience before we?
No, thank you just for your attention. I should say, at Duke, we have a new quantum center, Duke Quantum Center, and we are hiring at all levels. Essentially, we are looking for postdocs, PhD students, faculty. So please contact us if you are interested to coming to Duke. There's a lot going on here. Yeah, please just contact us. We have lots of open positions.
Wonderful. All right, Iman, thank you very much for the wonderful talk, and congratulations on the nice result and publication. Folks, thank you very much for tuning in. And with that, we will see you next Friday at noon Eastern Time.